Alright, so a quick demo to show you why n being a prime number is important. So this is taking the example from the previous slide. And in the previous slide, don't forget we have an IP address X and another one Y. And we ended up with, on the right-hand side of our equation, this. And I said that if you have n as a prime number, you're equally likely to get 0, 1, 2, 3, 4, 5, or 6. So anything from 0 up to n minus 1, you're equally likely to get any of those values when you take this equation. So why is that important? Well, if I evaluate this for a bunch of possible values for A4, so let's just try all possible values of A4 here. If I try all possible values of A4, and I end up with all of them telling me that these things are the same thing, what that means is that you can actually construct a pathological data set because all my hash functions map to the exact same bucket. So what I really want is for everything in this column here to be different, unique from one another. So let's just compute this. If A4 is 0, and I just fixed some values for X4 and Y4, if X4 is 3 and Y4 is 1, and I take that mod n, which is 7, what do I get? Well, 0 times anything is 0, so I just have 0 for the first one. Well, let's change that to a 1, and 3 minus 1 will always be 2, so I'll always be multiplying by 2. Mod it by 7, so what is 2 mod 7? That's 2. So far so good, no collision between those two. Now 2 times 2, mod 7, that's 4. It looks like we have a pattern of evens here, so maybe that's going to be a problem. Maybe we just repeat 0, 2, 4, 0, 2, 4, we'll have to see. Or 0, 2, 4, 6, for example. So we have, next we have 3 times 2 mod 7. How do I keep forgetting to write the 7? That's 6 mod 7, which is 6. And then next 4 times 2 mod 7. And that's going to be 8 mod 7, which is 1. Well, so that's nice. We've broken that pattern. We had 0, 2, 4, 6. Next is 10 mod 7, which is 3. And then finally 12 mod 7, which is 5. So all of these numbers did not collide. And that's all the possible values we have for A4 when n is 7. If n was 19 or any other prime, we'd end up with something similar. We could have these patterns where we go even, 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 but we're not going to have duplicate values over here. And this is the number theory that we're not going to cover in class, mostly because it's sort of out of my realm of expertise and not overly useful. I do think these examples are useful, so I hope you appreciate those. Well, maybe that's just because of our particular values of X4 and Y4. So let me put the values for the first column back. And now, maybe we just got lucky and it was because of these two values that things didn't collide. So let me change one of those and we'll go through the same process again. We're definitely going to end up with 0 for the first one, because you multiply anything by 0 and you get 0. When you do 1 times 4 minus 1 mod 7, well, that's 3 times 1, so that's going to be 3. And you can continue doing this, and this is what you'll get as a pattern. So again, no duplicates. So I'm not going to do a proof on this, but it turns out that these numbers don't matter for not having duplicates. It's this one. This one needs to be a prime number. Well, it wouldn't be very nice if I didn't at least show you why that might be. So let's use the same values here for X4 and Y4, and then same things over here, and just see what we get for patterns. Well, we get 0 again in this first slot. The next slot is 2, 4, 6, so it starts out the same way as we had before. But now, this is 8, and if you take 4 times 2, that's equal to 8. You take that, mod 8. Well, last time when we had modded it by 7, we got 1, but this time we get 0. So in fact, we're going to repeat that pattern. So what this means is that a lot of our hash functions are going to have the same collisions, which makes it easier to create a pathological data set. So what is it about 8 that doesn't work? Maybe it's just 8. It's not any it's not any number of buckets. It's just maybe 8 happens to be bad. Well, the problem here is that when you take 3 minus 1, that's 2. And it turns out that if 2 shares any factors with n, you're going to have repeats. So over here, we have a bad value chosen for our buckets here, but 4 minus 1 is 3, so we don't share any factors between the 8 and the 3. So we don't have a repeated pattern. So that's why we say that n should be prime, because it's not going to share any factors with what you're modding by n. Alright, so in summary, we cannot create a hash function that prevents the creation of a pathological dataset. It's not possible to do so. As long as the hash function is known, a pathological dataset can be created. So one cheap and easy way around this problem is to just make it infeasible to guess which hash function is in use.